because there is many example that when you have to ask, you have to use the recursion. You have to use the recursion. If the problem is not defined in a recursive way, it's not easy. It's not easy for you to find out a recursive version of that algorithm. Okay, and of course, in the case that we have only the recursive solution like the Tower of Hanoi and some other algorithms, if you have to use it, have to implement a function in the iterative way, it's not easy. Okay, so that is the thing we should know is recursion is not good. We have to we use it because we have to use it. Okay, and finally, they have one part in the book that tell you on like one of the two ways in order to remove recursion. The first way is we blindly analyze the recursion using the structure of the code, means the first line, second line, and third line, and we simulate the call stack of the system. Means after we call, we start where should we return. Means we have 5 lines, let's say, with few if else there, and we check if the return will be 5. We somehow simulate the go-to. We move to the life number 5 of that code in order to continue after we return from the nested call, the recursive method. So that way we have a way to remove recursion of all kind. It means we can do it for any kind of recursive function because it's just based on the structure of the function. That is the first thing. And the second thing is we can always remove recursion by design the algorithms in terms of like a to-do list. I put it to the stack to say, now we do it, the task we put in the stack, and after we finish the task on the top of the stack, you will move to the task below in the inverse order. Okay, that is the remove recursion. Okay, and I strongly recommend that you spend time and check and play with that kind of thing. Okay, so we have that is the recursion, and now just before we start, I will before we start a new section, I will say something about our midterm exam. Okay, so now the midterm exam, we will have like 90 minutes for your midterm. We will have the question from all the chapters from beginning up to the recursion. Okay, up to the recursion. Okay, and then we try to ask you to manually play some what we say some hand. It's been run some algorithm by hand. It's been I will ask you to fill the table. Say the first step 1, we have the value here, we have the stack there, and so on. What is the output of this stack? It means we do the sorting or finding or something else with the table. Okay, but on another part, I do want you to write some code or analyze some complexity of some algorithm or some solution. So you mean that that cover most of the work we have so far for the data structure and algorithms. Okay, so take care of that. You can bring handwritten notes with you, as many as you want, but must be handwritten. Okay, it means you have to write down. The goal of that is I don't want you to just bring the slide and without reading anything, without have a look at, without looking at the content. Means that I will not accept the photocopy one. Means your friend may write something for you and just to make a photocopy of that. I will reject that thing. The goal is clear. I want you to spend time to write down what you want to keep, what you want to learn. So that is the sum up the way that force you somehow to read and write down, and you have one time that pass through your brain on of the notion you want to do. Okay, so again, that must be handwritten. You can write as many as you want, you can bring as many as you want, but it must be handwritten notes. Okay, is it clear, everyone? Any question on the midterm? There will be no laptop allowed for this. What? You I don't know, you new problem or not? Of course you have new problem. No? I will not just check the content in the slide. You have to have some work that you have to play. I mean, you have to think and have to solve it, of course. Okay. As many notes as you want. Yeah, they do have some programming question for sure. So I've typed here as many notes as you want. Uh, 19 minutes with programming question for sure. Okay, any other things? Okay, is it clear? Yeah, yeah, that is in the library, means another block in the the central library. It's not in IU. Okay. No, it's not in the university, but in the VNU library, no? Okay, everyone, is it clear? Now we can move on. Yeah, including recursion. Chapters. Okay. Yep. Now let's start. So everyone, now we are moving to another topic. Again, it is not in your exam, but you must learn it for your final exam. Okay. Now advanced sorting algorithms. Okay. So what we try to do is now we learn another kind of sorting algorithms. You know, here we try to show you many sorting algorithms. It's not only because we want to show you the way to sort, but to show you the way that people can improve something, or that you can come up with some idea in the way they can do the same thing differently. That is very important for developers later on when you want to optimize something, when you want to do you want to improve something. You see the way that people think and the way people come up with the solution, and then that will have you to just give you some more idea to improve your work later. Okay, just give you some background. So now, well, we have the cell sort algorithms and the quick sort algorithms. We call it the advanced sorting algorithm, and you see the way they do and the performance, it will be better than the sample sorting algorithms that we have so far. And now I will try to just 1 second. I will try to put in this one, so it could be easier for you. Okay. Now we start with cell sorting. Okay. The idea is the cell sorting algorithms. Can you hear me now? Is it better somehow? I put in my headphone. Hello. Is it better? Okay, so everyone. So now, that's good. Thank you. So now we move to the shell sorting algorithms. This algorithm based on the insertion sort. Okay, is good for medium-sized array and faster than O(n) square. Okay, and now have a look at what we have. People recommend to use it. It's been now for insertion sort. If you remember, the way that we do insertion sort is we try to consider our array into the sub-array. Some of them are sorted partially, it means amongst themselves, and the other is not sorting. Is not sorted, and we try to insert it to the new position. Okay, and let's say we somehow sort the algorithms from the end up to this moment. Okay, and you see that we put everything in sorted order. Let's say we put it in sorted order already. And now as the last step, you will see that we have number 0. Okay, the number 0, the way we try to do is try to insert it into the sorted sub-array like this one. This is sorted, and if this is the smallest value, what we have is we have to say shift the thing to the left by not really shift, but we copy into the left. Okay, we copy it like this. Okay, and then finally we can put 0 here, and you see that kind of thing we would say, wow, it takes a lot of time, because we have to move 0 from here to the first position, and we have to do a lot of copy, but we not really need. Just like in selection sort, in selection sort, what we want to put 0 to the first position. That's it. Now people want to reduce the number of copying operation like that. Can someone tell me, or just sit down now and think about the way how we can say reduce the number of what? Copy in this case. What can we do about that? How can we remove the number of copy there? Just tell me, please. 1 second. Think about that. I will back in 1 minute because I want to leave the meeting and back so that I can see at least some icon with colorful icon. I quite I'm not really want to have the boring like icon this. Okay. Just 1 second and try to think, and I will back. I'm sorry that there's no improvement. I still have some like a rate scale icon. Sorry. Okay, but anyway, so what is it? So if you have to reduce the number, could be what could we do? So remove the key comparison. Okay, sure. Okay. Remove the key comparison from the loop and shift that element up. Okay. Yeah, it's not really clear how, but and now everyone. So people say that is too many copy, and the way that people say that now, what we do is we try to compare one to this element, and then one to this element, and one to this element. Okay, this one. That way, it takes time. And if we successfully, we move 0 somewhere here or here. Now, instead of just compare it in a small step like that, people say, why don't we make a bigger move? Means I will compare 0 with this one somehow, and now 0 with this one. That is briefly the idea. Instead of make compare to the next element, we want to make like a bigger jump with the hope that we can bring it to the first position with fewer number of steps. Okay, that is the idea of shell shock. Okay, and the idea is now we consider the sorting items not like breaking the array into 2 parts anymore. Last time we have this part is sorted, somehow sorted, okay, and this is unsorted, and we try to put it there. Now the idea is we will consider the array as many sub array. So we have this one, 3 elements like this, 0, 4, and 8 is one sub array. And what we do, we compare 8 and 4, 4 and 0. We do the insertion sort among 3 elements like this. And you see that if it by chance we have 0 here, in one comparison, I move it here. In 2 comparison, I move 0 to the first position. You see that we can bring the item to the corresponding position with fewer jump or few copy like this. And of course, we have to sort it like this, and we do it that way. We consider the first subarray. Here the second subarray is been 1, 5, and 9. Okay, the second and the third will be 2 and what? 2 and 6. Okay. Okay. And 3 and 8 in our subarray. So we have many small subarray. We do the insertion sort among them. Okay. With the step 3 in this moment, and then we do it again with the step is 2, or maybe jump back to 1. Finally, we do the last step in the sort algorithm is we do the insertion sort for the shell sort. So the bigger jump, just like somehow like the pre-processing, it helps us to move the object to the right or close to the right position. Okay, that is the idea for a cell sort. Okay, and now just to make a concrete example, we try to see here. We consider 3 subarray: 1, 0, 4, 8, 1, 5, and 9, 2, 6, and 3 and 7. Okay, and then we do the sorting. After all subarray are sorted, then they say it almost sorted. Then we finally make one sorting. It means we do the insertion sort for our array. Okay. Let's say let's try to do it. I will give you some number, and we try to do it to see what really means that way. Okay, here let's say we have some array 100, to something. Two, 3, 4, 5, 7. Say one more. 8. How many items do we have here? Okay, 9, 10. Okay, so for the first array, we consider this one. That will be, let's say, 0, 4, and 9. I will put some numbers to make it easier. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so the first subarray, what we try to do is we try to consider 0, we plus what? 4, and 8. That is my first array. Okay, and then my second array will be this guy. So this guy is this second subarray 2, 1, 5, and 9. Okay, and the third one will be this one, this number and this number is one pair, and last one we have this one. Let's put it this one color, this one, and this one. Okay, now we do the sorting. So we sort the first one. So we have considered 100, and we try to put. We consider this guy. We consider this. We consider this guy now. This guy, and this guy. Okay, and this guy. We consider 3 first element. So what we say, we try to insert 21 to the array of 100. So we copy 100 there, no, and we paste this one. Okay, and now we have the second one is second time we consider 10, and we try to insert 10 to the subarray of 21 and 100. So we could be 100 here. We say compare 21, so 21 here, and that's one. You see? Let's put it like this. Just remember. You see? Now to move 10 from the the index number 8 to the first position, we make just 2 copy. Before we had to copy 10 to this guy, this guy, this guy, this guy. Like we do it 9 times. Now we do it just 3 times or 2 times, and then we can take 10 and put it in the right position. Okay, and of course the array is not in a good format because we have to consider the second time we consider this guy, not this one and this one. Okay, so we consider it. We have 2 and 0. We move 0 here and we copy 2 here. No, so you see we can bring 0 to the first, the position number 1 has been the second position in just 1 copy. Okay, and now we have 8. We compare 8 with 2 and 0, we have nothing. Okay, that could be like that. And then we do it for the next round. We do 2 and 6. Okay, so for 2 and 6, what we have 19 and 80. So we put 19 here, 48 here, 47. Okay, it's just that's it. And now last one. Okay, you see here we have 3 and and 27. Is okay that way. And 27 and 28. You see, now we say we have almost sorted array. So let's put it all together. You see, that way we somehow reduce the number of copy we have to make to bring some number to the corresponding position. So we can bring 100 here and bring 0 back here with few comparison. And now we somehow sort the array. Now we apply, after that we apply insertion sort. Means we apply the one sorting. We call it one sorting. Okay, and now we just do it like before. We do insertion sort, we copy it there up, and then after that we have 18 and 10, nothing, so we put 18 there. We had 3, we try to insert 3. Of course we have to make some copy, and we had 3, and it's just like before. And now we have 21, there's nothing. We had 2. Of course we again have to make some copy, but at least you see the way that they do it like this, that help us somehow to reduce the number of copy. This is the one. Okay, and then we have this is in good position. We put it there, and then we had 28. Of course we have to make some copy. This one, and we have 100. We put it here, it's normal. And last one we have 8. Of course we cannot do anything better, we just have to make some copy. And of course, okay, so everyone, that's it. You see, is it clear for you? Everyone, is it clear? The way we do shell sort, you see? The others, is it clear? Yeah, that is the idea. You see that somehow it have us. Now, I want all of you to like practice a bit, no? Let's take some numbers. we can have a random numbers first, otherwise just do it. Number 1, 2, 3, 5, 6, 9, and let's say 10. And this is your work. You must do it. I put it 0 here, just to make it longer. Okay. Okay, everyone. So let's do like this. Yeah, for the moment, what we do so far, we do for sorting. If you remember the meaning of the for sorting, and then we do one sorting. And after this example, I will show you the way to split. Of course, that is a very good question. Then means if the array is like 1,000 elements, we should not start with 4, no? We should better start with 100 or something. That is a very good question, and I will show you the formula later on. But now let's try to do with this right. Okay, it's good, Tân. It's good. It is a good observation and question. Okay. No, okay. We will not do the copy to. We will not do the copy to another memory. Okay. We just virtually consider. It means we compare the index, the number index 0 and the number index 4, and we just swap between them. We don't need any extra memory. Okay. Got it, okay? Means we just one array, and we virtually consider break it into subarray. We virtually by consider only the number 0, 4, and 9 as a subarray. Yeah, we will not make any new, like we don't need any new memory for that. Okay. Yep. Sorry, I didn't move it. So please use this set. Please sort this, okay? And like when you finish. Yes, that's good. Thank you. And the others, please like, tell me that you are finished with that. Okay. The others, is it okay? Do you need any help on that? So for for sorting, what we do, we consider the first one, 0, 4, and 8. The next one will be, I put it that way. Okay, this one, and 5 and 9. Okay. And for next thing, we will put this one, 2, 6, and 10. Okay. The last one will be this one. And, okay. This one. So you see we have many subarray like that. Okay. The others, please like when you finish to tell me, please. It's good, thank you. Yeah. Okay. The others, just continue, and if you still have problem, please tell me. Okay. Okay. So we have like 60 of you here. So please do react to the message, please, again and again. Yeah, I cannot check your progress. Just tell me by like your message. Okay. It's good. Thank you. So now, okay. I hope that you now understand this one. So we just continue on this slide. Okay. So you see that we have the way of sorting, and they say that last step of this will be the insertion sorts. As you remember, if we do the insertion sort, for sure we will have the sorted array. Okay. The other kind of big jump sorting, we just have us to pre-process the data to make the array to almost sorted. Okay, that is the idea. Okay, and And now for the array of this is good, a good question from your friends. Remember Luận or someone else, okay, or Tân. Okay, we have this one. It makes sense to make a for sorting for 10 elements, but for like say 1000 elements, it's not clear, because for 1000 elements the jump of 4 is not good enough. Okay, because we want to make a bigger jump, we can save a bit more than that. So actually people have a formula for that, and this is the result of that formula. It's mean for 1000 elements, we start with some big number like 300 and something, and we continue with this one. Of course, these numbers is very important for the performance of the sorting algorithms. It means if we start from 1, the insertion sort. If we start 4, it is likely just one sorting. Okay, so people have to find the way, say, to find the best, like a rule to to divide the array to subarray, and we call it interval sequence or gap sequence. And Knecht is one, like a famous professor. Professor is computer science, especially specialized in algorithms. He proposed a formula. Is this one means that we just apply this formula for the sequence of steps. It means we start from number 1, and the next would be 1 multiplied by 3 plus 1. It means we have 1. The next number would be 4. Okay. Next number would be 4 multiplied by 3 plus 1. Let's say we have 13, okay, and so forth. Multiplied by 3, we have 40 something. Okay, so that is just the gap, you see, and just continue like that until we have the edge, it means the step is bigger than the size of the array, and we stop. And this formula this formula, you see that is one of the like a research based on experiment and measurement. They measure the performance. They try to find the best way or the best numbers to improve the sorting, and this one is one of them. Okay, and we see that let's keep it this for a moment, and then you see by the end of this one, you see we have many like different researcher in computer science in algorithms like this. They try to find out the sequence, the way to measure. And originally from the first author, they proposed that it would be h divided by 2, and later on people make another proposal, and you see that the algorithms finally they can measure the performance of that. We range from 1.5 n power 1.5 to n power 1 something like 1.1 something. Okay, you see that the performance improve. Okay, let's say we reach almost 1 here in some cases, and you see that is very good improvement, and that is say better than sample sorting algorithms. Okay, so you see that is the rule, and just one final step. I want you to say apply the formula like this one to find out the gap. If we have the this is just the inverse of the previous formula. So let's try to find the sequence of gaps that we have to do. If we have the array of 2000 elements, what will be the sequence of gap that we can use to divide the array to subarray? Okay, so please do it, and then you can have a break. Okay, so please do it. Apply the formula. It's just the inverse. The origin is the h equals to h multiplied by 3 plus 1. No, that is the origin, and then we have it. Okay. So tell me, like, what will be the sequence, and you will see. So what will be number, please? Someone? Just very straightforward. No, just apply the formula. What we have. Calculation, and we have it. What? 2000 minus 1 divided by 3. So we have 666. Okay. Next step will be 666 minus 1 divided by 3. So we have 2, 1 something. Okay. So we have 2, 2, 1 minus 1 divided by 3. We have 7. Okay. So 1, 8. Okay. 24, 1 divided by 2. Sorry. 11 and so forth. So we have 10 divided by 3. We have 3. And then last one we have 1. Okay. Everyone, is it clear? Write the formula. Is it okay, everyone? So now let's take 15-minute break. Okay. Just just think about that. And now after the break, I will move to the implementation of that. Okay. So here, if you want, you can have a look at that. All items. Otherwise, see you in 15 minutes. Okay. Yeah. See you then. Okay, everyone. So let back to work. So now, please have a look at the implementation of the shell sort algorithms. You see that this is the original sorting algorithms. Where is my pointer? You see, this is the original instruction sort. We do the out loop, and then we try to make the long as a temp from the out, and then we compare the current value is mean the out with the previous value in the subarray, and just if it's bigger and we copy. Okay, the only thing that we need to change in this one is we will not just decrease one, but we decrease h, and that's it. Okay, you see here, every time we reduce, we make it -1. Okay, now let's say we make a minus h, and that, and we make one extra while loop. You see, this is the insertion sort. Okay, if h equals 1, we have the insertion sort. Okay, and after that, you see every time we do the update, h equals h minus 1 divided by 3, and we do it again and again until we reach s is 1 or 0, then we stop. You see, the implementation is quite straightforward, but just by one observation that we can make, say we can wait with the array virtually and make it jump like make a bigger jump to compare, and then we can reduce the number of copy operation, and we can have the chance to move the item to the right position, close to the right position faster. So that way we have the shell sort. You see, now when you sit back and think about the way that they improve the algorithms, you see, most of the time they based on just observation, and we sit down to see what can we do on the basic operation of that algorithms. In this algorithms, we have the comparison, and we have the copy or the shifting. See, people can reduce the number of comparison in this case because we based on the like the insertion sort, we based on the properties of the sorted subarray. No, if we sorted, we can have a chance to reduce the number of comparison, the insertion sort, and then we want to improve the copy, so we try to make a bigger jump. See, that is the idea for the shell sort, and hope that you see next time when you have some problem at hand, try to again check on the number of the basic operation that you have to do, and then you try to see the thing how you can improve it. Of course, it takes time. It's not easy to find out that kind of thing, but that is why people say we do research. People sit down and try to think how we can do it better, and that finally have a new algorithms. Okay, everyone, is it clear for the selection sort, for the shell sort? Okay, is it clear for you? Any question on that? Okay. Otherwise, we will move to the next like algorithms. This algorithms is we call it partition. There is a process. It's not a sorting algorithms. It's just a process of doing things, but that will have us to perform, or actually what we say, that is the key operation for the quick sort algorithms. Okay, now have a look at that and check what does it mean by that. Okay. So now what we have is we have there is the underlying mechanism of quicksort. It means quicksort actually is a partition operation. It's a quite useful operation. The idea of this one, the goal of this one, we don't want to sort anything. Okay, we don't want to sort. Okay, but we want to divide our data into two groups. One group that is bigger than a given value. Another one is smaller or equal to the given value. Okay, so again, let's say here in example. So we have the set of items like this. There is our pivotal value. We want to say that everything on the left will be start from this one. Will be smaller than the pivot value, and everything on the right will be bigger than that pivot value, and that's it. We don't want to sort amongst item on the left. We don't want to sort item on the right. We just want to say on the left will be smaller than my value, and on the right will be bigger than my value. And my question for you, first of all, is that is it always the case that we have two sets, one on the left, one on the right? It means, is it possible to have 0 item on the left? It means there is 0 item that is smaller than my numbers. Is it possible that way? Is it possible to have like no value that is smaller than my numbers? Yep. That's totally possible. Because it depends on the value I select. Let's say I can select my number is -1 somewhere over there. My number is very small. Means everything here will be bigger than my numbers. And then that moment I will say the array is just belong to the right side of my partition algorithms. Means everyone is bigger than my numbers. There's nothing on the left. The left in that sense means the left sub array, the virtual one. Okay, and the same goes for the opposite direction. If I put my numbers is that high, means everyone will be smaller than my numbers, and no one will be on the right. On the right means virtually on the right, on the side that they are bigger than my numbers. Okay, that is some remarks that you should remember. And now, if we have the idea like this, okay, and if we have, let's say, if we have some numbers, let's say I put it like this, let's just I will draw some pie chart again just to imagine. Okay. Now, if I have my chart like this, let's say this is my pivot value. I want to work with this so that we can rearrange the items in my data set here to the left and to the right as the requirement. Means everyone on the left will be smaller than my value here. Or everyone on the right will be bigger than my numbers. Now, I ask you to think about how we can put it in order. This means how we can partition our data set using this like a pivot value. This one here. This is my pivot value. How I can partition my array. Is there any way that I can partition my array like that? Think about that. Is it possible to do something? Okay, now let's look at this algorithms, okay, to see what can we do with that. Okay, now the idea, the way that we can implement it is quite straightforward. Let's say I will put some numbers here. I will take one item in the left, okay, and then I have another item on the right. Okay, what we want is that, assume that we have, I will open my Word file again. Assume that I have this one. Okay. Let's say that is my numbers. That is my array. This one. Okay. Now I will have two pointer. One on the right, on the left. Another one on the right. I will put it like this. Okay. One on the left and one on the right. Okay. What we want. Say we want to say, I will say my let's say I will put my numbers. I just make it simply, I just randomly pick it. Now it could be anything. I put it 40. Okay, it's my pivot. It can be anything now. Now, what we want to make sure that everything on the left, if we start from the left, this one must be smaller than my number. If there's something on the left very bigger than my number, what we want to do, we want to move it to the right. No? It should be to move to the right. Where should I give it? Of course, I can always put 80 here. Okay. I can always put like this. But of course, for the array, we have to shift things. It's not good. What people do is this one. After I found an object, a number on the left that needs to be moved to the right, I stop there. I go to the right. I will check whether or not I have my numbers. There is 0. There is smaller than 40. What we want to move it to the left, no? Because on the rightmost is mean it must be smaller than bigger than my by default value, but now it's smaller. We want to move it to the left. And now up to now, what should I do? Can you say something? We will hello? What should we do? Swap them. Yes, that's it. The swapping will save a lot of work. We don't have to shift things to the right and then we shift things back to the left, no? This is the way we want. That's it. We swap them. It's good. Okay? After we swap them, we have a new thing. After we swap them, what we got 0 here. 2 could be the same. And now we have this. And we are good with that. So we don't need to work with that number anymore. So after we swap, we move to the next number, 2. We want to consider 2. From the left again. On the left, we try to find something that is not, is not correct and we want to move it to the right. That is our task. So 2 is smaller than 40. It's okay. We don't care. Keep it there. It is in the right side already. We move here. 80 or 48. Okay, I need to move it to the right. That is our goal. And now from the left, what we have, last time we stayed here, we put it here. Okay, 29 is smaller than 40. And it must be on the left. Okay, again, we swap them. Okay, that is our task. So we do it again. We have 2 here. Swap it, 29. Anyway. The order is not changed. Okay. Okay. And last time we stopped here. Now we move our pointer here. And the number I need to consider is this number. We start from the right, from the left first. So 90. Okay, again 90 bigger than my numbers. I will swap it. Okay, make it move to the right. After we found an item, it's okay. So last time we have here. Now we consider 67 is bigger than 40. There is nothing to do with that. So we have 28 is smaller than 40. See, move it to the. This means we find a candidate. Okay, so that's it. And then we swap it again. The other thing is no, it's not changed. There's one thing you should remember is that we don't care about the item in this side. Okay, this one, as long as these numbers is bigger than 40, we are okay. We don't need to sort them. We don't do anything else. Just continue our work. Okay, I don't care about that. So I move to this one. This is smaller than my numbers. Again, I want to move it to the right. Okay, and now we consider this one. This one is smaller. Okay. Oh, sorry, I make a mistake. Sorry, I make a mistake here. Now 7 is smaller than 40. We are good with 7. Okay, we are good with 7 because it's smaller than 40. So we consider 1. 1 is smaller than 7. It's okay. We continue. Now 39 is smaller than 40. It's okay. We move here. Okay, and then we say okay. We have 99 and need to move to the right. We stop there. And then we continue on the right. Last time we are here on 27. We move here and now pointer. Now we move it to this position. Okay. But what happened? Do you remember what happened? Is that we have this guy. Oh, it's not good. This one. Okay. This guy cross this one. Okay. When we have the left pointer cross the right pointer, what does it mean? What does it mean, everyone? When we have the left pointer cross the right pointer, what do we have? From the beginning, as you remember, we start from the left here and we start from the right here. And after the left and the right cross each other, it's crossed already here. What does it mean? It means what? This means that it means that we already visit all of the elements of the array. Okay, we start from the left, we start from the right, and then if we cross, means we visit everything. And then at that moment, the pointer here, the right pointer, people say that will be the first number, no, of the right array. Okay. So if you back here, this is, we call it the partition value. Partition means the leftmost item of the right subarray. Again here, in the leftmost, this means the first item of the right subarray. Okay? And that is the position. We know that everything on the left here is belong to the left array, means everyone here is smaller than 40. On this one, everyone here is from this number to the right will be bigger than 40. This is what we have. This is smaller or equal to 40. This is what we know. Okay? And this one is bigger than 40. So that's it for the partition. See, is it clear, everyone? Now everyone, again, I want you to play with this because we will use this one to do the sorting. Okay, so now let's try to play with these numbers. Oh. One this mark, we'll erase it. Okay, so everyone, so please use this one. Use this one as the example. Now try to do the partition. Let's say I will say my numbers is now I want to use, because the pivot value could be anything. I can use any numbers that we want. I will use, let's say 28. One numbers in my array as a pivot value. Okay. Now try to do it, everyone, please, and like when you finish. Okay. So do the partition. As in partition the array. Okay. And like when you finish. It should be easy. It's good. See. Yeah, swap them. There's one thing actually. We always start from the left. Okay, we try to find. It's been after your first step. The second step we consider number 2. Okay, we will not move our right pointer in the same time. We just move the left pointer first. So we move from 2. We move to 40 what? 47. Okay, and then we found 47. That is the number that we want to swap, and then we go to the right and move our right pointer. Okay, step by step like that. It's good. See. The others, is it okay? You need some help? And on the others, please like it when you finish. We have like 60 of you here, but around 10%, it's been 6 of you do react to the question. Okay, please do it. React when you finish, everyone. It's good, thank you. Okay. So if you want if you finish, please like it. When it 10, I will move on. The other, if you want me to wait for you a bit, just put it in chat box, okay? Otherwise, I will move on, okay? So let's take the example, the result of she, and what we see. Okay, I'll put it here. There's one thing I want to share with you, this one. Just take the result of she, and then we continue with this. Okay, everyone. Now, let's say that we are. What is that? To do this. Try to do something. Okay. So everyone. So you see that the way we do the swapping. Of course, there is some small thing that is not really what we want. Okay. What is it? Eraser. Okay. So everyone, there's one thing I will tell you, that say here we will try to swap it. No, swap left, right. Of course, you can say this is bigger than, this is smaller than. Okay. But this one, there is one thing. There's one thing. I want you to check. Let's say here we have my numbers 28. Okay, and this is my pivot value now. This is my pivot value at the beginning. Okay, and now can you tell me something about this? Please observe this position. What we have so far is everything on the left of this position is our partition. No? Remember that is our partition. Our partition means the one is the first element of the right subarray. Okay. What we have so far is that everything on the left of this partition will be smaller than 28. Okay, do you agree? The partition. And everything on the right will be, that depends, okay, it could be like this and in the opposite direction. But anyway, we keep it like this as the result C, and we see everything on the right of this will be bigger than 28, or bigger than equal than 28. So think about that. Is there any special about that position? Is there any special thing, special property about that position? In a sorted array, what do we have? In a sorted array, let's move back to here. Let's say we have something totally random. We have something. This is our array. Okay. And now later on, when we sort, it will be like this. No? And this number, okay, what we can say about the left and the right of this number if it inserted, if it inserted, it is final position in the sorted array. And if we don't know anything about this, what we can say about the position of a number and the left and the right of that in a sorted array? What we have in a sorted array? Compare this one and this one. In a sorted array and in this, what do we have? No. We let's say we have any numbers in any, let's say in any number and in any array. If it is sorted, what we have? We cannot say the three elements left, that element in the right is sorted. No, we cannot say that. Of course, in sorted array, everyone is in the right order. It's okay. What we can say is that if, yeah, that's good. That's what we want. Look at this. Look at these numbers. 28. We don't care about the others. But at that moment, if we know that I am in the position that everything on my left is smaller than me, everything on my right will be bigger than me. That means that I am in the sorted position. No? Everyone, do you agree with that? It's good, Nick. It's very good. Everyone else, do you see that? I don't care about the order amongst the thing on the left. I don't care about the order of the thing on the right. But if my position, I know that everyone on the left will be smaller than me. Everyone on the right will be bigger or equal to me. Means I am in a good position. I am in a good position. Do you agree, everyone? See, that is a very important observation. And that is the idea for the quick sort algorithms. Okay? Okay, remember that. Now, if the pivot value is mean 28 in this concrete example is in the partition. Remember, partition position is mean the first element on the right of the leftmost element of the right subarray is mean this partition, the one that divide our array into two parts. That position, if the pivot value are in this position, it means it is in a sorted position. Okay, you see now, people will use that partition operation in order to implement the quick sort algorithms. Just based on that idea. Okay, it's a very smart way to do the sorting. Okay, now is it clear? Now we move on now. For the partition, the algorithms, just look at it at home. It's quite straightforward. Just left, right, and that's it. Okay. Now, the complexity of this, of course, just to check the partition for each element on the left and on the right, we move from the We move from the left to the right. If it meets in the middle and it cross, so we stop. Means each element in the array we just go through it one time. So the complexity of the partition operation is on. Okay, do you agree, everyone? On means each element we just have to consider it one time. Okay. So it ends step. That's it. Okay, we not do anything two times. Okay. So when now, if you agree with that, now let's move on to the quick sort algorithms. Okay. The most popular sorting algorithms. Let's say it is fastest in some cases. On average, is it n log n? It's just like the merge sort algorithm, but the on average, no, it means sometimes it works, sometimes it's good, but on average, we not say this one. It depends on many situations, but on average, this one. But it's different from merge sorts. Is that the merge sort algorithms you have to use extra space. Now we don't need any extra space for that. Okay. Now the idea of the quick sort is very basic. If you remember, we partition the array into subarray. We do the partition, this one, and that's it. And then we partition it again and again. Nothing special, just partition again and again. Every time divide by 2, partition. Okay, now have a look at this. These algorithms is like this. At the beginning, if we unpartition array, okay, what we want, we take the last number. We check it and use it as the partition pivot value. Okay, we take it, use it as a pivot value. And for the moment, after we take it, we skip it. Okay, we don't care about this number anymore. We start to partition this one and this one from the beginning to the second last element without the pivot value. We don't care about that, just because we will use it later on. And then we partition. We partition the array. So we have 2 subarray, right? So the left and the right. And in the last moment, so we will swap the pivot value and we put it to the partition position. That's what we want. Because if we put pivot there, we may move it around. We don't want to touch the pivot, because anyway we want to bring the pivot to the partition position. Okay, we bring the pivot to the partition position. That is what we want, the last step. So again, take the last number at the pivot value, try to partition the array from the first to the second last element. Okay, and then move or swap this pivot value with the partition. Put it in the partition position. It means if the partition, after you partition, you get something else. I don't know. It could be just do and you will see. Could be any other numbers. We don't care. But then finally we will move 36 at the pivot, put it to the partition value, and then in that moment, as the observation, we see 36 will be in the sorted position because we put the pivot value to the partition position. Okay, and after one step like that, after one iteration, what we get as an invariant for the quick sort is we can make or can move one new element to the sorted position. Okay, and we do it n time, so we will have what? Do it n time, we will have n element in the right position, and that's it. Okay, everyone, is it clear? Is it clear? Yep. Now, let's try to do it. Okay? Let's try to do it. And you see the magic of the quick sort algorithms. Okay? Let's try to do it with, I will start with something that is, let's say, I will do it with this number. Okay? I try to copy it and then you see. Just 1 second, I will try. So I have 42, 80, 63, 12, 94, 27, 78, 3, 30, and this one. Okay, so here we are. Up, where is it? Okay, here we are. Now I will take this number at the pivot value. Okay, I will keep it here. Don't touch it. Okay. Now I will do partition at 36 as my pivot value. So we have here. This is bigger, ready to move. No. So I will move it there. I say that we should move it. I go to the right, and we see 50 is okay. So now I say this one should move and this one should move. So what we have 3. Okay, we have this one is not changed. So this one, this one, this one, this one, and then we have 42. Okay, and we have 50. Now what we do, we have this, we move to this. This is bigger than my numbers. It should move to the right. Okay, it's okay. And then I move here. I check here. This one is bigger. I will not touch it. This one is smaller. I will swap it. No. As a result, we have here. Sorry, this 27, 63. Okay. 48, and then we have 97. Say 89. Okay. And I continue. Of course, the remaining will be like this. If you want, keep it. And now I consider this guy. This guy is bigger than my numbers. Okay, I will ready to move it. This is bigger. It's okay because it's on the right. No. So this one should swap, and that's what we have. 3. This one. This one. This one. Okay. Okay. Now it's ready. What we can do is now what we want, we can do the swap. We put 36 to this one. Oh, sorry, it's not finished yet. So here, of course, I know it's finished. I move to 63. 63 is bigger than my pivot, and it should move to the right now. And from the top, I have this one. I move it here. Of course, it's crossed already. So I will stop, and as I stop, you see 63 is the partition position, no? So everyone on the right here is bigger than or equal to 36. Everyone on the left is smaller than 36. Okay, what I want to do next is I will move or swap that. This one, and I swap it. No, I will put it 36 here. Okay. And the last one is, you see that the last swap is okay because anyway 63 is bigger than 36 and it's on the right. It could be anywhere on the right, no? Could be anywhere on the right, still easy, okay. But that moment we have this one is in the right position. Okay? Okay, everyone? Now, what we say, we don't need to care about 36 anymore. It's okay. We are ready. It is in good position. So now what we need to do is to work with the two subarray, this one and this one. Okay? Okay. So like we have 3 elements. There's many updates. Is it okay, everyone? Up to now, is it okay? Is it clear? Hello, is it clear? Everyone? The others, if you have any question, please ask me, okay? Otherwise, let's continue. So we have this, yeah, is you have the 2 subarray. Now we work with the first small subarray, this one. So we have 3, this one, of course, you can always use the partition again. You will see, you take 12 as a partition value. We have 3, is smaller, it's okay. We have 27 is smaller, is okay. And then finally we swap it. We have 3, 12, and this one. It means like a straightforward. You see, a very simple step, and we have sorted because it's just 3 elements. So that element, we don't need to sort anything else because this one is sorted. And by chance, it's not by chance, it is a very smart way to do because we break it to smaller parts. And this one, just 1 element is in right position already. We don't need to do anything with that. So we have 3, 4 of them in a good position. It's meaning correct position already. That is the magic of the quick sort. Okay. Now we consider this subarray. We work with this subarray. Okay. Now what we do, we take this one as the pivot value. Okay. Then what we do the comparison. So this one is 94 is bigger, and we swap it with 50, no? And then we continue with this. The 89, the bigger than 63, and the other side we have 42. So we swap it with this. We have this guy. So next time we consider this guy. This is bigger, okay? But the thing will be like the left and the right pointer cross already. So we're done with the partition, and what we know so far is this is the partition position. The partition position is the first element on the right, that on the right subarray that bigger than this one. Just write down again, you will see. Okay, so you see that there is the thing, and now the last step we do is we swap it. No, we swap this guy with 63. Okay, and now what we have, 63 is on a good position already, and because everything on the right of that will be bigger, everything on the left will be smaller. Okay, and now we work with this subarray again. It's just 2 elements. We can easily do it with many basic things, and we always do have it. So we're done with that. We had 3 elements. We do partition or whatever you want. You will have it. Let's say I need to swap it somewhere, or I don't know. Let's say this one will be the swap, and this one is this. Okay, because this is there's nothing that's smaller than 87 there, so we put 87 here because the partition here, the left side of that is nothing, the right side of that is all of this. And of course we have 2 elements. From 2 elements, last step would be just a last step thing. Okay, everyone, so that's it. You see, there's somehow the magic. What we have here. You see? That's it. Everyone, is it good? That is quick sort algorithms. Any question on this? Hello? Okay, otherwise now let's do one like one something on your own, okay? Just to practice. Let's try to do it. Okay, I think that's it. So let's try to do this quick sort algorithms, everyone. And like when you finish. Okay.
So please like when you finish, okay? Hello. Why it take you so long? Is there any problem with that? The others, do you need any help on this? Hello. Hello. Are you there? Okay, everyone. So I hope that now you get the idea of the quick sort algorithms. Okay. Now what I want you to do at home, okay, at the homework, and to see that what happened if we have the array in the inverse order. So let's say we have this one. What happened if we have this? Okay. Okay, everyone. So try to see, this means try to run the quick sort algorithms if the array are in descending order. Okay. Otherwise, that's it for today, and good luck for your midterm exam. Okay. I'll see you then. Bye. If you have any question, you can always ask me. Okay. Bye bye, everyone. Yeah, see you. Thank you. Bye. Thank you for your participation and very active in class. Thank you. Bye bye.